Hello students.
Hello students.
So what we're going to be doing today, Mr. Leong?
We are doing the gaseous state.
Yes, let's go! Wow, Mr. Leong, there's so much space inside this balloon.
Yeah, that's why you can compress it, right? It's just like a brain.
Yeah, a bit.
A lot of space. Okay, so I think we'll start off a lesson by taking a look at the three different states of matter. Now, you've learned this in primary school before, so we're going to run through this fairly quickly.
Yeah.
I'm just going to focus a lot more on the arrangement and movement of the particles.
Yep.
Mr. Tim, can you run us through that?
Okay, yeah, I want you guys to imagine, let's say this is a solid particle or a particle. All right, in a solid state, the particles are very, very close to each other and they are fixed. They just vibrate and by their fixed positions and they are actually orderly arranged as well. Okay, so you can imagine, right? Now in liquid state, so say if I heat it past its melting point, now this is where the arrangement becomes less orderly, right? It's a bit more messy now, okay? And now they also slip and slide over one another.
So it's slightly further apart and it's going to be in a slightly disorderly arrangement. Really.
Exactly, yes. So no longer very, very ordered. Now in gaseous state, when I heat it past its boiling point in the gaseous state, the arrangement becomes a really, really messier now. It's all over the place and they're zooming past each other at high speeds.
Yes, so now it's going to be in a disorderly arrangement and they're going to be very far apart, right? So of course, as the name of the chapter suggests, we are going to focus solely on the gaseous state, and let's delve into some of the main important aspects of the gaseous state, right? Okay, so for gases, there are certain physical quantities that are important. Mr. Tim, can you remind us what those are?
Yeah, we have four of them. We have pressure, volume, temperature, and amount. And when I mean amount, I mean number of moles, right?
Now, let's take a look at a more layman's understanding of pressure.
Yep.
So, Mr. Tim, what do you understand by the term pressure then?
Oh, pressure is what I feel when I'm teaching you students in class. Oh, it's super pressuring.
Okay, that's not what I meant. In a more scientific manner.
Okay.
So let's take a look at if you are standing at the sea level, right? So 0 meters above sea level at the ground. What kind of pressure are you feeling? Now, it is going to be coming from the air that is above us. And that is going to be coming from the atmosphere, right?
Right.
So that's why we call the pressure, the units, right? It's going to be on one atmosphere. So let's say if you decide to go up to Mount Everest,
Okay.
right? And
Wow.
can you tell me whether if the pressure you're experiencing should be higher or lower than 1 atmosphere?
Well, if I manage to climb all the way up there and survive, okay, then the amount of atmosphere that I have now, the amount of gas particles is lesser.
Okay.
So therefore pressure is lower.
Oh, that's right.
Yeah.
So in general, 1 ATM is a unit for pressure.
Yeah.
But normally we don't really use ATM as a unit, right? What do we use?
We use pascals, right?
Okay.
We use pascals.
So what we do is we're going to have this conversion over here, 101325, right? Now this number don't have to memorize because it's going to be part of the data booklet. Okay. Okay. So now, Mr. Tim, can you share with me a little bit more about pressure in the chemistry sense?
Hey, sure thing. So what I'm going to show you guys here is a box, okay? It's an empty box right now. So you can see there's a pressure gauge at the top right-hand corner, okay? You can see that currently it's in 0 pascals, like pascals, so use SI units for pressure, okay? Now, notice what happens when I introduce one gas particle into the box. And I want you guys to focus on when the particle hits the container of the box, hits the wall, okay? It is that point when it hits it, the pressure should go up, all right? Take a look. Okay, so one particle right now, wait for it, bam! And you can see the pressure went up to 12 kilopascals, okay? So this is basically what pressure means. Pressure is the force that a gas particle exerts when it hits the wall, okay? And that basically is what pressure is. All right.
That's right. What about volume then? So I think volume is quite simple. It is just the space that the gas particles occupies. So in the context of this animation, it's just going to be the container, right? Now, one important thing is going to be about the units. So going back to the notes, right? There are two units that you are very comfortable with: the cm cube and the meters cube. The conversion, you must know it well. You also must pay attention to the fact that the dm cube is right smack in the middle. So between cm cube and meters cube is going to be 100,000, but for dm cube it's going to be 10 power 3, right?
Okay, I'll run you guys through temperature and amount, and that's it. So temperature is basically a measure of how hot, how cool
Thank you.
you are, okay? So you guys are very comfortable with the units of temperature. It is degrees Celsius, but take note, is that SI?
No, that's not.
No, the SI unit for temperature is Kelvin. And how do we convert degrees Celsius to Kelvin? We just go to the degrees Celsius and we add 273. So 0 degrees is basically 273 Kelvin. Very easy. And of course, Mr. Leong, if I have 25 degrees, can you do the math for me?
Okay, so if it's 25 degrees, I'll add 273 to it. You end up with 298 Kelvin.
Well, quick math, man.
Thank you.
Yeah, 298 Kelvin, okay? That's it. All right. Now, last but not least, we have amount, and you guys should know this by now. Amount always refers to number of moles, okay? And the SI unit for moles is just
Moles.
M-O-L, okay?
Now, what we're going to do now is we're going to take a look at all these physical quantities and how do they relate to each other.
Yeah.
Oh, what? Oh my gosh, Mr. Tim, what are you doing?
I'm trying to see how volume affects pressure.
Okay, but you didn't really have to do that to demonstrate that, right?
Oh yeah.
Let me explain to you what's happening. Okay, so just like we're trying to compress the balloon.
Correct,
Yeah,
correct.
so the volume is going to decrease, right?
Yeah.
Can you tell me what's going to happen to the pressure of the gas inside the balloon?
Well, if I decrease the volume, then the gas particles will hit the walls more frequently, right?
Okay.
So my pressure should go up.
That's right.
Yeah.
So this tells me that the volume and the pressure, they are going to be inversely proportional.
Right.
Okay? So that's what you're going to see over here. The V is going to be inversely proportional to P. Now, mathematically speaking, right, you tell me that, hey, I can actually rewrite this as an equation. V equals to K times over P, where K is going to be a constant. Okay? Now, what's going to happen next is that I can actually cross multiply the variables, and you're going to end up with this very important relationship, right? P times V equals to a K, right? Now, if I go back to the animation over here, right? Now, let's see what happens if I decide to halve the volume of your container, right? Can you please halve it for me, Mr. Tim?
Sure. So you guys can see first things first. You can see in this gas container now, the pressure, top right hand corner, is 592 pascals. So what I'm going to do now is decrease the volume of the box to 5 meters, or 5 nanometers, 5 meters. Now, when I let go, Mr. Long, do you think the pressure should go up or go down?
So like we said, decrease in volume, the pressure is going to increase.
Correct. Okay. So do you think it will be exactly 2 times?
Yes, probably.
Bam, 1174. So that's almost about 2 times. Okay.
That's right. So that is going to illustrate the relationship over here. So we can actually generate equation that relates the numbers before and after the change in the variables. Right? It's going to be given by here. P1V1 equals to P2V2, where 1 indicates the initial state before the change, and 2 will indicate the after, right? After the change has been exerted. Okay,
perfect. Yeah. Now, let's take a look at this experiment. We're going to take a beaker, fill it with hot water, take the balloon, touch the hot water. Look at what happens. The balloon's volume increased in size. We'll begin. So as you guys saw in that cute little experiment that we did just now, when I increased my temperature, right, so the balloon became hotter, the volume actually increased, right? So now we're going to talk about how volume and temperature affects each other. So we'll start off with this. Increase temperature, increase volume, and a bit intuitive, right? But we'll break it down step by step, okay? So what I have for you here is a very cute little box, and the pressure of the box is 1 atm, all right? So there's 1 atm in the box, 1 atm also outside, the surrounding pressure. So when I increase temperature, by right, the gas particles will hit the walls more frequently, right, Mr. Long?
That's right.
And the pressure should go
up.
Yeah. So when the pressure goes up, I'm going to write here, pressure goes up when I increase temperature. So say now the pressure is now 2 atm. Now, does a box like this, Mr. Long?
I don't think so. No pressure, right?
Correct. So the box doesn't want to be higher pressure than the surrounding pressure. So what's the box going to do now is this. It will try its very best to reduce the pressure. And how do we reduce pressure, Mr. Long?
So I think they're probably going to increase the volume then.
Correct, exactly. Because we just saw this in Boyle's law, right? For me to reduce the pressure, then I have to increase the volume, okay? So for the box to go back down to 1 atm, to be the same as surrounding, I want to decrease my pressure. So I will increase my volume, and the pressure will now drop back to 1 atm. And the box loves this. And this is why when I increase temperature, there will be no net change in pressure, because it still remains 1, but it will result in an increase in volume, okay? And this is basically your Charles' law. And nicely put, volume is therefore proportional to T. So once again, we're going to bring in that proportionality constant. We have learned this in math. V equals to KT, where K is just a constant. So once again, we're going to bring all the variables to one side. So V over T, and all the constants on the other side equals to K. Now this means that V over T is always constant. Initial V1 over T1 equals to V2 over T2. Perfect. Okay?
So this formula, just have to pay attention that the temperature must always be done in terms of kelvins.
Exactly.
Right?
Yeah.
Okay?
Okay. So remember, he's Boyle, I am Charles.
Okay.
We are going to combine. Okay? And what we're going to have here, Mr. Long, can you take it away?
So if we combine the Boyle's law and the Charles' law, we're going to end up with this thing called the combined gas equation, right? So it's going to be given over here. So once again, you tell me that the 1 represents the initial state, the 2 represents the after state. Now, shall we take a look at the work example to illustrate how we're going to apply this formula? Okay. So we're going to start off with 1 pressure, 150 atm, kilopascal, and there's a volume over here, 300 cm cube. And what we're going to do is we're going to decide to change the volume to 180. We're going to compress it. Okay, so it's our V2 over here. So what we normally do over here is, because there's a change in one of these physical quantities, I'm going to write out the combined gas law first. Right? Now, because this was done under the same temperature, you'll notice that the T's will all get cancelled away. Okay, so you're only left with just the numerator. P1V1 equals to P2V2. And we're going to sub it in. right? So submit the numbers, and finally you can get your P2 to be this number over here. Okay. Now there's something very special about this formula is that the units, normally we have to change it down into SI units, right?
Correct.
Yeah, but for this case, we don't really have to do that. We just need to make sure that the units must be consistent. Now that means that if I start off with an ATM, the final answer will also be an ATM. That's nice, right? If you start off with a cm cube, then your V2 will also be in a cm cube.
Makes sense.
Okay?
The next law that I'm going to talk to you guys about is Avogadro's law, not Avogadro's law.
Okay.
Okay. Now we learned a little bit of this in motion stoichio in J1 in Sec 4 as well. We learned this, right? 1 mole of any gas, I don't care about the identity, 1 mole of any gas occupies 24 dm cube, but at a fixed room temperature, at a fixed set of conditions, right?
Okay.
And the conditions was room temperature pressure, 20 degrees Celsius and 1 atm. So, Mr. Long, remind me again this formula. If I increase my moles into 2 moles, how does my volume change?
I believe it will double as well.
Right, so it's proportional, right?
That's right.
Yeah, so when I increase moles, my volume also increases by the same amount, okay? So it's proportional. Now, but all of this was done at the same temperature, constant pressure. We kept it the same, okay? So this is basically Avogadro's law. Volume is proportional to N. And once again, we can write that proportionality constant, again, V equals to Kn, right? Where K is a constant, bring the variables to one side. So V over N, bring over, leaving you with K on the right hand side. So once again, if V over N is always constant, V1 over N1 equals to V2 over N2, okay?
So far we have gotten all the 3 laws, right? ABC, right?
Yep.
So A is Avogadro, okay, Boyle's law and Charles' law.
Okay.
So what we're going to do is we're going to combine these 3 equations together, and you're going to end up with this particular relationship. You'll notice that V is going to be directly proportional to NT over P over here. And of course, the moment it's proportional, I can always introduce a proportionality constant. In this case, I'll use the letter R. Okay. Now, from here, this is going to be a very important relationship. I will do a bit of manipulation, and I'm going to end up with this equation over here. PV equals to nRT.
Pretty.
A very popular formula. Now, this is called the ideal gas equation. Now, which means that only if you are an ideal gas, then you are going to obey this law very nicely.
Yeah.
Okay. Now, one of the important things that you must learn how to do is to apply this equation in exam. And a lot of times, if you look at your friend's scripts or something like that, you'll notice that a lot of the careless mistakes was made because of the units error.
Yeah.
Now, this is a physics equation, which means that all the units must all be in
SI.
That's right. So that's why we want to take a look at the units again. Remind you again what are the SI units. For pressure, it is going to be pascal. For volume, it's going to be meters cubed. And the number of substance is going to be in terms of moles. And the T must always be in terms of Kelvin. Right? Now for the R, which I call it a constant, right, is going to be known as the molar gas constant. It always has a fixed value and a fixed unit of this.
Okay.
Now, this number is actually found inside your data booklet, so you don't really have to memorize it. Now, Mr. Tim, can you run me through the derivation of the molar gas constant then?
Hey, of course. Now, to derive the units of R, I'm going to assume this, 1 mole of a gas, so I have the N given, and at standard temperature and pressure, which means 1 bar, okay? But remember, SI units for pressure is in pascals, and 1 bar, it is 10 to the power of 5 pascals. And also temperature, standard temperature, it is 0 degrees Celsius. Make sure you convert the degrees Celsius into Kelvin, right? SI units again. The volume in STP, you guys should know this. 1 mole of any gas is 22.7 dm cube. So convert dm cube into?
Meters cube.
Yeah, because SI units again, all right? And we're going to take all of this, and we're going to plug this into this pretty famous formula, put everything in, and you get your R, which is 8.31. Take note of the units here, joules per Kelvin per mole. And if you ever forget the units, just flip to your data booklet, okay? It's all there.
Now, what happens if you decide to do this at RTP instead?
Okay.
Right? So if you use 24 dm cube, do you think you get the same answer, Mr. Tim?
Pretty much, because we know that R is constant no matter the conditions, right?
That's right.
Yes.
So therefore, it actually works for any kinds of conditions,
Yes.
right? You'll always get back the same constant.
Correct.
Now, some of us, right, may be a bit more funky, right? So if I decide to go and introduce certain new physical quantities, the equation for the ideal gas may change slightly, but it's still the same thing.
Yeah,
Right?
yeah.
So what I'm going to do now is I'm going to do a bit of modification. Now, this N over here refers to the number of moles. I'm going to replace it with one of my famous mole formula. I'm going to change it to in terms of mass over molar mass. Okay. So I'm going to achieve this over here. And what I'll do is I'm going to switch the positions of the V as well as the MR. Now, what's going to happen over here is you're going to achieve this particular formula. The MR goes to the left and the V is now in the denominator. Now, pay attention to this particular fraction over here. This is mass over volume. And for those that have done physics, you'll know that this is known as the density of the gas, right?
Smart, yeah.
Okay, so I'm going to use rho over here to denote the density. So this, after a bit of manipulation, you should be able to end up with this particular equation. So this equation is still the ideal gas equation, just that it's introducing molar mass as well as density of the gas together.
Good stuff.